Hello everyone and welcome to the third part of our topic on Strand 2.2. In the previous session, we discussed about certain gas laws, namely Boyle's law, Charles' law, Avogadro's law, ideal gas equation and combined gas law. So today we are going to be looking at different other gas laws and see under what condition we are going to be using those formulas. So the first gas law for today we are going to be looking at is GAY-LUSSAC'S law, which is the law of combining volumes. So basically what this law states is that whenever chemicals combine chemically, especially with gases, okay, since we are talking about kinetic theory of gases, so we are only going to be focused on gases. So when gases combine chemically, their volumes are going to give you the volume of the product if it was a gas as well. Okay, the only thing that we have to keep constant is the temperature and the pressure. So in simple terms, what it basically means is that let's say there is an equation, there is a reaction taking place between hydrogen gas and oxygen gas producing water. So assuming that all the chemicals here are in gaseous state, so the volume of the hydrogen gas, the volume of the oxygen gas, when they are combined together, okay, that is going to give you the volume of the product. So in order for us to determine which of the two volumes we are going to use in the ratio, we are going to use something known as a limiting reagent. So to find the volume of the water, we can use ratio like this. Mole of hydrogen gas is to mole of water, or mole of oxygen gas is to mole of water, depending on which of the two reactants is the limiting reagent. So whichever is the limiting reagent, that is the one we are going to be using in the ratio. So let's look at an example and see how we can use a limiting reagent to calculate the volume of a particular product. Now in this reaction, we are having 50 ml of carbon monoxide, which is reacting with 20 ml of oxygen. And the reaction is made to go to a completion at a constant temperature and pressure. We are required to calculate the volume of the carbon dioxide produced. So to begin with, we must have a balanced chemical equation. Now once we have a balanced chemical equation, we are going to calculate the limiting reagent. Now remember, we are calculating the limiting reagent. Reagent simply means a reactant, the chemicals that are mixed together. So we are going to have a mole ratio between the reactants. So this is what we are going to be doing. To find out which of the two reactants is a limiting reagent, we are going to see how much of them are required in the reaction and how much of that is really present in the reaction. Okay. So let's look at carbon monoxide. According to the equation, 2 moles of carbon monoxide is going to react with 1 mole of oxygen. That information we can get from the mole or the coefficient that is in the equation. Okay, so if you're looking at the equation, you can see the number 2 in front of carbon monoxide. That 2 is the moles of carbon monoxide, while in front of oxygen the number is 1. That is the mole of oxygen that is required for this reaction to proceed. So if 2 moles of carbon monoxide reacts with 1 mole of oxygen, what is going to happen if we have, let's just say if we are using 50 ml of carbon monoxide, how much of oxygen is going to be required? Okay, so you can see the ratio now. If carbon monoxide is 2:1, and if we have 50 ml of carbon monoxide, then how much of oxygen is really needed in the equation? So according to this, let's do the crossover method. And according to the crossover method, the 2 is multiplied by x. So we have 2x is equal to 50 ml multiplied by 1. So we have a ratio like this. 50 is equal to 2x. So you find the value of x. The x is going to give you the moles of oxygen required. Okay, so we will have 25 ml. So what it basically means is that in order for carbon monoxide to react with oxygen, since according to the equation we have 2:1, if 50 ml of carbon monoxide is present, then we require 25 ml of oxygen. However, only 20 ml of oxygen is given. So what do you think about the amount of oxygen then? The amount of oxygen that we have in the reaction is less compared to the amount that we need. Therefore, oxygen is the limiting reagent. There is another way you can work it out. Sometimes instead of finding how much of oxygen is needed, we can work it the other way around. Okay, so to find the limiting reagent, we can use the mole ratio again. The mole ratio between the reactants. So we have 2:1. Okay, so let's say if 20 ml of oxygen is used in the reaction, how much of carbon monoxide is needed now? Okay, so we are swapping the equations around. So in this case, if oxygen is 20 ml, then how much of carbon monoxide is going to be needed? We're again going to do the crossover method where the X is going to be multiplied by 1 and 20 ml is multiplied by 2. Okay, so we are going to find the value of X, which is going to come to 40 ml. So that basically means that if 20 ml of oxygen is required, then we will need 40 ml of carbon monoxide. Okay, but how much of carbon monoxide is given in the equation? In the reaction, we are having 50 ml of carbon monoxide. So what does it tell you about the reaction and the quantity of the chemicals involved in it? Well, since we need 40 ml and we have 50 ml of carbon monoxide, that basically means that carbon monoxide is an exceeding reagent. That means it is more in abundant. Okay? In our calculation, we are only required to find the limiting reagent. Alright, so now that we have calculated our limiting reagent, which is oxygen, let's see in the next part how we are going to use this limiting reagent to calculate the volume of carbon dioxide. Okay, so now that we have calculated our limiting reagent, let's find the volume of the carbon dioxide in the equation. So to find that out, this is the ratio we are going to be using. The moles of the limiting reagent is to the mole of the product. So go back to the equation once again and see what is the mole ratio. So between oxygen and carbon dioxide, which is our unknown, the ratio is 1:2. Now, if we have 20 ml of oxygen in the reaction, how much of carbon dioxide is going to be produced? So let's work that out. That is 20 times 2 and we have our volume of carbon dioxide as 40 ml. So students, this is how we use a limiting reagent to calculate the volume of a product. Okay students, so now let's see the next calculation method, which is called DUMAS method. This method is used to calculate the molar mass of a volatile liquid. A volatile liquid is any liquid which can vaporize easily because it has weak intermolecular forces of attraction. So if you recall, we have learned this particular formula under ideal gas equation. So if we substitute the n, that is a variable in this equation, okay, as moles is equal to mass over molar mass. So instead of n, if we put these variables in the equation, how will the equation read as? So the equation is going to read as PV is equal to mass times R times T divided by molar mass. Now, since our objective here is to calculate the molar mass of the volatile liquid, if we make Mr the subject of the formula, the equation can be rearranged as Mr is equal to MRT over PV. So, in order to calculate the molar mass of a volatile liquid, there are a few variables that is needed. Okay, number one, we need to have the mass of the gas. And the only way we can do that after doing the experiment is to obtain the mass of the flask, empty flask, and then ms of the mass of the flask plus vapor, which will give you the mass of the vapor. Okay, R is a constant, which is 8.314. Temperature of the boiling water has to be taken, the water which is the water bath, okay, the temperature at which the liquid has been vaporized, that is measured in Kelvin. and then pressure, which is measured in kilopascals, and then the volume of the gas inside the vessel. So having all these variables will allow us to calculate the molar mass, which is measured in grams per mole. Now let's see a video, okay, which is going to tell us the experimental procedure that is used to calculate the molar mass of a volatile liquid.
In the DUMAS method of determining the molar mass of a volatile liquid, we will start out massing an empty 125 milliliter Erlenmeyer flask, a small piece of aluminum foil, and a small piece of copper wire. We will then add approximately 5 milliliters of the unknown liquid. We will cover the mouth of the flask with the aluminum foil. We will use the copper wire to hold the aluminum foil in place. We will place a small pinhole in the top of the aluminum foil. We immerse the flask in a beaker of boiling water. The liquid inside the Erlenmeyer starts to boil and vaporizes. As it vaporizes, it pushes air out of the pinhole. Eventually, all the liquid vaporizes, and the flask is filled with just enough vapor to fill the flask at the temperature of the boiling water. Once the liquid has completely vaporized and the vapor has reached the temperature of the water bath, we will remove the flask from the water bath. The vapor inside the flask will condense to a liquid. When the flask is cooled to room temperature, the liquid that has condensed was the amount of vapor that would fill the flask at the temperature of the boiling water bath. We will now mass the flask, the liquid, the aluminum foil, and the copper wire. Since we know the mass of the empty flask, aluminum foil, and copper wire, we can get the mass of the liquid. We will determine the volume of the flask, which is also the volume which the vapor occupied at the temperature of the boiling water bath. We will remove the copper wire and the aluminum foil. We will fill the flask completely with water, and we will pour the water into a graduated cylinder. We will record the volume of the water.
Let's look at one example as to how we can calculate the molar mass of a particular gas when we are given the following variables. So we are having a 256 milliliter flask, okay, so that's our volume, which is filled with a gas at 97.505 kilopascal, which is the pressure, and at 100 degrees Celsius temperature. Now this has to be converted into Kelvin. The mass of the gas is given as 1.675 grams. So now in order to calculate the molar mass of the gas, we all have the variables that is supposed to be used. So now let's put it all in order. Okay, so we have the mass, the temperature in Kelvin, the pressure, and then the volume. R is a constant, so we don't actually have to write it. So now we'll just have to have this equation around. PV is equal to MRT over MR. Make MR the subject of the formula, and it should read as MR is equal to MRT over PV. Okay, let's substitute our values now. So if we substitute our values, you can see how the calculation is done. Now at this point, students, it is very important that if you are doing the calculation at the numerator first, and you're going to write that answer down, then I suggest that you do not round off your answer over here, okay? Because if you do that, then your answer right to the end is going to differ. So 1.675 times 8.3134 times 373, okay? If you multiply all these three together, do not round the answer off. You can leave your answer in as many significant figures here, because once you calculate your MR, numerator divided by the denominator, your answer should exactly be 208.10 grams per mole. If you can work it out yourself. If you round off your answer too early, your answer would not be 100% accurate, okay, as what is expected. So the final rounding off should always be done at the last stage. So I hope you have understood how you are going to relate your ideal gas concept into a DUMAS method. Okay, the only thing that has changed here is instead of N, we are using M over MR. The next concept that we are going to be looking at is Dalton's law of partial pressure. Dalton's law of partial pressure is basically telling us that partial pressure, okay, of a particular gas, if it is present in a mixture, is going to be the pressure exerted by the gas if it were present alone in the container. So what it basically means is this here now. Let's look at this scenario. So if we're looking at this particular picture, okay, in this particular setup, you can see that the steam particles are exerting a particular pressure of 0.8 MPa. Now, if this steam were present in a mixture, okay, so if you have a mixture of steam and air, the pressure of the steam will still be 0.8 MPa. So whether steam is present alone or in a mixture, the amount of pressure exerted by the steam is going to be the same. Okay, and then we look at air. Air is alone in this container, exerting a pressure of 0.2 MPa. When air is in a mixture, it will also exert the same pressure of 0.2 MPa. So we can say in a mathematical expression that the pressure of steam plus the pressure of the air is going to give you the pressure of the mixture. So when we write the equation, it will read as such. The total pressure in a mixture will be equal to the pressure of a gas A plus pressure of gas B and so forth. Okay, so the total pressures of each gas is going to give you the sum of pressure of each gas will give you the total pressure in a mixture, and these individual pressure is known as the partial pressure. Now if you are given the partial pressure and you are asked to calculate the total pressure, then it's going to be very simple. You just have to add them up. However, if you are given the total pressure and the mass of each gas, how will we calculate the partial pressure? So to do that, we are going to put using this equation here now. The partial pressure of a particular gas is equal to the moles of the gas divided by the total moles times the total pressure. Keep in mind, you will be using this formula if you are given the mass of individual gases and the total pressure. Okay, so let's look at some examples. Okay, so in this particular question, we have 1500 ml flask, which is 1.5 liters, containing 400 grams of oxygen and 60 grams of hydrogen gas at 100 degrees Celsius. What is the partial pressure of each gas? And then you have to calculate the total pressure. So now you can see this question is slightly deviating from the information we were given earlier on. Let's look at our variables. We are given the volume, the mass of oxygen, the mass of hydrogen, and the temperature, which is 100 degrees Celsius. And we have to find the total pressure. Okay. So now, which equation are we going to use which uses these variables? Okay, so let's check out what do we have. We have the volume, we have the temperature, and we have the mass. So from the mass, what can we calculate? From the mass, we can find the moles. So we have the volume, we have the moles, we have the temperature, and we need to find the pressure. So the equation that we are going to be using is going to be the ideal gas equation. So let's work this out first. We are going to first find out the moles of each gas. So the mole of oxygen will be equal to mass of oxygen, which is 400, divided by the molar mass, which is 32, and you get the mole as 12.5 moles. Calculate the mole of hydrogen gas. Okay, so that's 60 grams of hydrogen divided by 2, and you get 30 moles of hydrogen. Now, let's work out the partial pressure of oxygen first. So to do this, we have to find our parent equation, which is PV is equal to nRT. Okay, so we need to make pressure the subject of the formula. And when we do that, let's substitute our values and see. So the mole of oxygen, okay, which we have calculated here is 12.5 moles, which is here, times the R, which is a constant 8.314, multiplied by temperature 373. So 100 degrees Celsius plus 273 will give you 373, divided by the volume in liters 1.5. Okay, so you get your partial pressure of oxygen as 25.84 times 10 to the power 3 kilopascal. Okay, my advice to you here is, students, that if you get your answer in a lot of significant figures, which is as such here, then try to convert this answer into a standard form so that you end up having fewer significant figures with the 2 decimal place answer. We do the same thing for hydrogen now. Okay, when we calculate the partial pressure of hydrogen, we use the same formula, PV is equal to nRT. Now, since the volume is same because they are both in the same flask and the temperature is the same, the only thing that will change is the mole. So, when we substitute these variables to find P, we will get the mole of hydrogen, which is 30. The mole which we calculated here is 30. So, that's the 30 that is put here, times R, which is a constant, times temperature divided by the volume. And we get our pressure of hydrogen as 62.02 times 10 to the power 3 kilopascal. Now, since that we have the partial pressure of oxygen and the partial pressure of hydrogen, let's look at the second part of the question. What is the total pressure? So the total pressure basically is the sum of partial pressure of each gas. So that would be equal to the partial pressure of oxygen plus the partial pressure of hydrogen. And this is how we can work it out. So the total pressure comes to 87.87 times 10 to the power 3 kilopascal. So earlier on, we have seen how Dalton's law of partial pressure can be used to calculate the partial pressure if we are given the mass of a particular gas and certain other variables. Okay, we are going to now look at the second version of Dalton's law, which is applicable whenever a gas is collected over water. So for those gases which are insoluble in water, the best method of collection will be downward displacement of water. Okay, now if you're looking at this scenario here, this is one example by which a particular gas can be collected over water. So when this gas is collected over water, okay, which is this region here, that is where the gas is going to be collected. Most of the water which is used in the collection part is going to exist as a vapor. So we can say that when we are looking at the pressure of this system here, this is going to be due to the pressure of the gas which is collected plus the pressure of the water vapor. And that sum is going to give us the total atmospheric pressure. So you will be given in questions the total atmospheric pressure. And when that is given, be rest assured that this pressure is due to the sum of pressure of the gas that is collected plus the pressure of the water vapor. Now, if you recall from our earlier lessons that in a closed system, so this is a closed system, okay? In a closed system, the pressure that is exerted by the gas over the water or over the liquid is known as saturated vapor pressure. So we can rearrange this equation and it will read as atmospheric pressure is equal to the pressure of the dry gas plus saturated vapor pressure. Saturated vapor pressure will always be given to you and you will always be given the atmospheric pressure. So you will be required to calculate the pressure of the dry gas first. Let's look at a couple of examples now. Okay, so in this example, we have some oxygen gas collected over water. Your clue is this bit here. Okay, so if you are given the information of so and so gas collected over water, that is your clue. So as soon as you read this part here, you have to calculate the pressure of the dry gas using the formula that we have just learned. So let's see. We have the temperature, we have the pressure, and we have the volume. So this particular pressure that we have, okay, this 101.3 kilopascal, This pressure is known as the atmospheric pressure. So when we calculate the pressure of the dry gas, we use this particular formula. Pressure of the gas plus SVP is equal to atmospheric pressure. You rearrange the equation, make pressure of the gas the subject of the formula. So atmospheric pressure is 101.3 minus SVP, and you get your pressure of the gas as 99.1 kilopascal. So this is the first set of working that you have to do whenever you come across a question where it says some gas was collected over water. Okay, so let's continue from the previous question. Now, once we have our pressure of the dry gas, how will we calculate the volume of the gas at STP? So let's see what variables we have now. We have our pressure 1. Now, this pressure 1 is 99.1 kilopascal, not 101.3, because the 101.3 was the atmospheric pressure. P1 is your pressure of the dry gas. So we are going to put pressure of the dry gas now. The volume is 0.02 liter. The temperature is 292 Kelvin. And at STP, what do we know? We know the pressure of STP. We know the temperature at STP. And we'll have to find the volume at STP. So let's make, okay, so this is the equation we use. Let's make V2 the subject of the formula. This is the combined gas equation. Okay, so when we make V2 the subject of the formula, this is what we get. Let's substitute our values now. So for V2, these are the values we are substituting. And we get our volume as 0.02 liters. Now, one of the most common mistakes that students do here is this here. They fail to change the atmospheric pressure. It is very important that when you calculate the volume of the dry gas, okay, for a particular gas which is collected over water, you must calculate the pressure of the dry gas, and that is going to be your P1. Okay. Now, the last bit of Dalton's law is this equation here, which we have learned previously. If you are given the total pressure and the mass of individual gases, and you are asked to find the partial pressure, this is the formula that we use. So let's see one question. This is the kind of question that will be given. You are given the total pressure here, which is 105 kilopascal, and you're given the masses of the following gases. Okay. So now when we calculate the partial pressure, our step number 1 will be to find the moles of each gas. Find the mole of nitrogen, okay, the mole of oxygen, and the mole of carbon dioxide. So once we know the moles of individual gases, our formula requires the total moles. Okay, just go ahead and find your total moles. That will come to 0.6 mole. Okay, so now let's do our calculation. Let's start off with nitrogen. Find the partial pressure of nitrogen. So the formula says mole of the gas, which is nitrogen, divided by total moles times total pressure. So let's substitute. The mole of nitrogen we have calculated here, 0.125 moles. So that's the mole that is put here. Total mole is 0.6, so that goes as a denominator, times 1 of 5, which is our total pressure. So the partial pressure of nitrogen will be 21.88 kilopascal. We'll do the same thing for oxygen now. We have the mole of oxygen divided by total mole times total pressure, and the pressure of oxygen comes to 65.63 kilopascal. Finally, you find the partial pressure of carbon dioxide. Substitute your variables, and it will come to 17.50 kilopascal. You will know that you are on the right track if you are able to add all the partial pressures, and it will give you the total pressure. So when you add the 3 partial pressure, it should give you 105 kilopascal. However, in our case, we will not get exactly 105 because we have rounded off our answers here. Okay, but you will get a value which is closer to 100. So if you add the 3 up, you will get 105.01, which is good enough because we have ended up rounding off the answers. Had we used our original answers, then we would have 105 kilopascal exactly. So that's one way of cross-checking your work to see whether you have done the calculation in the right way or not. time for the quiz. Let's see. All right, ready for the question, students? So question number 1 for today. How many liters of carbon dioxide will be produced by burning 5 liters of methane with 8 liters of oxygen? Your answer? The volume of carbon dioxide is 4 liters. Question number 2. Your answers? And the last question for today. Well then, students, I hope you have enjoyed your lesson as well as much as I have enjoyed teaching them. So we will meet in the next part of the video, which is going to be the last part for this particular strain, where I will be discussing about the concept on calculating the concentration of various solutions. So take care, keep revising your work, keep updating your work. Bye.